In this video, we're going to finally learn how to solve exponential and logarithmic equations, both with and without graphing utility. So we don't have a lot of objectives, but we want to make sure that we look at an extensive variety of logarithmic equations as well as an extensive variety of exponential equations. So this video is a little bit longer than some of the others because there's just a lot of different varieties of things we might run into that I want to make sure we cover. So first we need to just talk about what an exponential equation is. An exponential equation is just an equation in which the variable appears in the exponent. So a simple example might look like 3 raised to the x plus 2 equals 5. Because the variable shows up in the exponent, it's an exponential equation. When we're trying to solve exponential equations, we try, if we can, to isolate the exponential expression, the base and the exponent, on one side of the equation. So when we say exponential expression, that includes the base and the exponent. Try to get that on one side of the equation. That's not always possible. We'll look at several cases in which that's not possible at the start, but if it is, that's where you want to start. Once you've done that, you want to take the logarithm of each side, either the natural log or the log base 10 or any base that you want, then use laws of logarithms to bring down the exponent. Basically that last property of logarithms that we looked at that allowed us to move the exponent of the input and make it a coefficient on the logarithm. And then we want to solve for the variable, and depending on the type of equation we're left with, that might be done any number of ways. So the first few examples will be, at least the first one example will be fairly straightforward, and then the rest will get a little more complicated. So if we're trying to isolate the exponential expression on example 1a here, 2 to the 3x equals 3/4, that's already done. We've got base 2, exponent 3x alone on one side. So then the next step is to take the logarithm of each side. I'm just going to do the natural logarithm. The natural logarithm. So the natural log of 2 to the 3x equals the natural log of 34. You can use log base 10, you can use log base 2, whatever you want. I'm going to do that. And then I'm using that last property that says I'm going to be able to move this exponent that's an input for a logarithm and make it 3x times the natural log of 2. And on the other side I have natural log of 34. And now this is really just a linear equation because natural log of 2 is a constant, natural log of 34 is a constant. So I just want to figure out how to get x by itself on one side. So x would be the natural log of 34, and then I would divide by 3 and divide by the natural log of 2. So it would look like that. X equals the natural log of 34 divided by the quantity 3 times the natural log of 2. That's an exact answer. And they also ask for an approximation to the nearest hundredth. So that you would need to use your calculator for. So let's go to natural log of 34. And then we want to divide by 2 factors. So we need parentheses, 3 times the natural log of 2. And, oops. Close those parentheses. So we get about 1.69, well, 1.70 if we round to the nearest hundredth. Because the 9 would round up to 10, and then we'd have 1.70. Alright, then, already in the next example, we're stuck on the first step. Isolate the exponential expression. Well, there are two exponential expressions, and in that case, we're not going to be able to isolate them. So instead of isolating the exponential expressions, we'll go ahead and take the logarithm of each side. And now we can use the property of logarithms that says, okay then, let's move that exponent down. Make sure you put parentheses around the first one when you move it down, because you want the whole group times the natural log of 10. And on the second one, we'll move the x down. This one's more complicated at this point because we have x's on both sides. So I guess what I would do is distribute everything. So I'd have natural log of 10 minus x times the natural log of 10 equals x times the natural log of 6. And then I would get all x terms on one side. So that means I want to maybe add x times the natural log of 10 to both sides. So on the left, I'll still have my natural log of 10. And on the right, I'll have x times the natural log of 10 plus x times the natural log of 6. And the reason I wanted to do that was so that I can factor out an x. And then I will have x in one term only. Natural log of 10 plus the natural log of 6 there. And then I'll divide by the natural log of 10 plus the natural log of 6. I'm just going to rewrite it on opposite sides, but it's certainly equivalent. So there's an exact value. If you want to use some properties of logarithms, you could. We could say that's the natural log of 10 divided by the natural log of 60. Make sure you don't cancel these natural logs and say that it's equal to 10 over 60. Natural log isn't a factor, it's a function applied to 10 and then a function applied to 60. So we can't reduce that yet. But that's an easier form to use on your calculator if you want to do that. So natural log of 10 divided by the natural log of 60. Looks like about 0.56 to the nearest hundredth. So here's exact, here's approximate. On this one, here's exact. Either one of these is fine. And here's approximate. But when there's an exponent involving the variable on both sides, we're always going to be wanting to distribute and then move all the terms with x to one side, all the other terms to the other side, and factor out an x to get through it. The next one, we can isolate the exponential expression because there's only one, and the key is to keep in mind this 10 cannot be multiplied with this base. We can't make this 30 to the x plus 2. That would be changing the base of the expression. So instead, we need to divide by 10 on both sides. So we only want the base and the exponent on one side. So we'll have 3 to the x plus 2 equals 2. And then we'll take the logarithm of both sides. So I'm going to do base 10 this time, just for something different. It doesn't matter which base we do, so I'll do 10. And the reason we do that is to be able to move that exponent down. So now we'll move x plus 2, and because there are two terms, be careful to put parentheses around it so that we can distribute. we want that whole group multiplied by the log 3. And then at this point we can either distribute or just divide both sides by log of 3. Let's do that. That's probably a little easier. And then subtract 2. So we would have x equals log 2 divided by log 3 minus 2. So again, you could have natural log of 2 divided by natural log of 3. That would be fine. Or if you want to, you can even write this as the log base 3 of 2. But in the first form, it's easier to evaluate on your calculator. So any of these are equivalent, and those are both exact. Either one is fine. And using this one on your calculator, log 2 divided by log 3 minus 2. We get about negative 1.37. All right. The next one has base e, as you can see. When e is involved as the base, you might as well use the natural log. It just kind of makes sense. So let's do that right away. We can see that the exponential expression, the base and the exponent, is already isolated. So right away we'll take the natural log of both sides, or the log base 10, or the log base 5. But since e is the base, the natural log, which is the log base e, that makes sense. At this point, you can remember that the log base e composed with e to a power is just going to give you that power back, because you would be composing a function and its inverse. Or you can do the same thing we've done before. Move the exponent down, multiply by the natural log of e, and then remember that the natural log of e is the exponent you put on e to get e, and that's just 1. So we've really got 3x squared minus 1 times 1. So we want to solve for x. We'll add 1 to both sides. And then divide by 3. Make sure you don't make this natural log of 7. The 1 is added after we take the natural log of 6. So we'll have x equals, be careful about this, positive or negative square root of, I'm going to write it this way, 1 plus natural log of 6 over 3. And then we want the approximate values. So I'm going to do natural log of 6 plus 1 over 3. I'm going to do the square root of that. Looks like 0.96 to the nearest hundredth. So either positive or negative 0.96 would be the two answers. All right, so example E here is more complicated because we've got the fraction, and then in the denominator of the fraction we've got our exponential expression. So first we want to try to isolate that if we can, or at least get it out of the denominator. So we could multiply both sides by the LCD, which in this case is 1 plus e to the negative x. That's going to look like cross multiplying basically. So we'll have 8 equals 5 times 1 plus e to the negative x. And we can see that we should be able to isolate this exponential expression because we can divide by 5 and subtract 1. Eight fifths minus 1, that's just 3/5. And now we've isolated that exponential expression. We've got it by itself on one side. So we can take the natural log. Let's do that since our base is e of both sides. Move that exponent down. And remember that the natural log of e is 1. Since e to the 1 is 1. So we just have negative x equals natural log of 3/5. So we'd want to divide by negative 1. So we'd have x is negative natural log of 3/5, which is fine. Or you can say, well, that's a negative 1 as a coefficient. So if you wanted to, you could do the natural log of 3/5 raised to the negative 1, which would just be the reciprocal of 3/5, so the natural log of 5/3. That's fine too. So any of these are fine. This is fine. That's fine. I'm trying to show you the various forms of your final answer, because when you're doing homework out of the book and you're looking at the solutions, or even on my math lab and looking at the solutions, you might have an answer that looks different but is equivalent to the given answer. So I just want to emphasize that there are so many different forms of these answers because you can use properties of logarithms to rewrite them in so many different ways. So always maybe grab a calculator and type in your answer and then the answer that's given and see if they are actually equivalent, if they don't look the same. So there's our exact answer and then the approximate answer. Looks like 0.51. All right, so far I would say we've looked at what are kind of standard or more basic exponential equations. Now we're going to take a look at a few that are a little trickier or just a different type. And the first pair here are what are called quadratic type, and we'll see why in a second. Actually, let's talk about y right now. So when I see this 3 to the 2x and then 3 to the x, notice that one of the exponents is just double the other. So really I can think of this as 3 to the x squared plus 3 to the x equals 2. So notice I have like this quadratic pattern, something squared plus that thing equals a constant. So it's not exactly quadratic because it's not x squared and x, but it's an expression squared and then that same expression in the middle and a constant. So when we have this quadratic type where we have an exponential expression showing up one place and then that same exponential expression squared in another place, that's what we call quadratic type. And in that case we want to get a 0 on one side, so subtract 2. And then try to factor. This we should be able to kind of reverse FOIL. To get 3 to the x squared, we would have 3 to the x and 3 to the x. To get a negative 2, we're going to have a 1 and a 2 with opposite signs. To get a positive 3 to the x, we want a plus on the 2 and a minus on the 1. So now we'll have a factored left-hand side equal to 0. When we have a product equal to 0, we can set the first factor equal to 0 and the second factor equal to 0. So with 3 to the x plus 2 equals 0, we could have 3 to the x equals negative 2. But the graph of 3 to the x looks like this. And negative 2 is down here. Three to the x is always positive, right? It's never going to be negative 2. So there's no solution there. 3 to the x can't be negative. But over here, 3 to the x equals 1, we can say, oh, well, x has to be 0. Because 3 to the 0 is 1. So there's only one solution to this particular equation, but the way we were able to solve it was, again, getting a 0 on one side, factoring, and then setting each factor to 0. Okay. The next one is even trickier. It's kind of a quadratic type in disguise. Let's first rewrite it like this. E to the x minus 12 over e to the x, rewriting e to the negative x as 1 over e to the x. To clear that fraction, we would multiply both sides by e to the x. And now we can see, well, we have e to the x squared. So now it's looking more like a quadratic type. Minus 12 equals e to the x. Get a 0 on one side. Maybe rearrange the terms so that this e to the x is in the middle. And then we'll try to factor it up here. We know we'll have e to the x and e to the x. To get a negative 12, we could do 6 and 2, or 3 and 4, or 1 and 12. Probably 3 and 4 will give us the right middle term. So let's do a 4 with a minus and a 3 with a plus. That'll give us our negative 12, and then it'll give us a minus e to the x like we want. So now we've got e to the x plus 3 is 0, and e to the x minus 4 is 0. This will be similar to what we just saw. So we'd have e to the x equals negative 3, or e to the x equals 4. And again, same as what we saw, 3 to the x can't be negative 2. E to the x can't be negative 3 because e to the x is always above 0. So that's not possible. But for the other side, we do natural log of e to the x equals the natural log of 4. X times the natural log of e is natural log of 4. So x is the natural log of 4 because natural log of e is 1. It's fine to jump straight to here. If e to the x is 4, then x has to be the natural log of 4. But if you need these steps in between, that's fine also. I guess they didn't ask us for the approximate solutions on this, but if we wanted to, we could grab a calculator and get the approximate value for natural log of 4. All right, then a few more that might involve even a little bit more creativity. Example 3a here, let me rewrite it so you can actually see it. We've got 3 raised to the 2 over log base 8 of x And on the other side, we have 27. And one technique that you can use is if you can rewrite both sides with the same base, then that would allow you to equate the exponents. So since this side is so complicated, I'm hoping that I can just rewrite the other side with base 3, which I certainly can. 27 is 3 cubed. Since the bases are the same, the exponents have to be the same. So that would imply I'm not dividing by 3, I'm just saying the exponents have to be equal. Oops. So we can just equate the exponents. 2 divided by the log base 8 of x equals 3. Then if I cross multiply, I'll have 2 equals 3 times the log base 8 of x. Multiply both sides by the log base 8 of x. Then try to get this 3 out of the way, or I could move the 3 up as an exponent on x. Either way, I'll do 2/3. Like this, 2/3 equals log base 8 of x. We still need to get to just x, so we need to switch to exponential form. We saw that in previous videos when we had basic, a real simple logarithmic equation like this. Switching to exponential form is key. So the base is 8. The exponent 2/3 put on 8 should give us x. So officially we're done, but let's rewrite that as cube root of 8 squared so that we can get to just an integer value. Cube root of 8 is 2, so 2 squared. Looks like x will be 4. So the first key is to rewrite both sides with the same base. And then if the expressions are equal and the bases are equal, the exponents have to be equal. And then go from there. Example B here, we can see we've got right now a sum equal to 0, and some terms and both terms have some factors in common. So let's try to, we'd rather have a factor, or a product, excuse me, equal to 0. So let's factor out what we can. In this case, that would be what, x squared and e to the x. So we have x squared e to the x times 3 plus x equals 0. So we have 3 factors officially, x squared, e to the x, and x plus 3. Excuse me, when we have a product equal to 0, we'll have x squared equals 0, the first factor, or the second factor, or the third factor could be 0. The first one gives us x equals 0 as a solution. The next one, we could try to say the natural log of 0 is x, but remember the natural log only takes positive inputs, so that's not going to work. There's no solution. Or you can think about the graph the way we did before. The graph of e to the x is always above the x-axis, it's never touching the x-axis. Whichever way you think about it, we're going to get no solutions. And then the last one, x would be -3. So you get those 2 solutions, x equals 0 or x equals -3. And again, the key is if you've got a 0 on one side, you want to try to have the other side factored. So a product equal to 0 is useful. And then example C here looks a lot like a quadratic form, but it's not quite as obvious as it was in some of the others. We've got 9 to the x minus 3 to the x minus 6 equals 0. These expressions have different bases, but we could rewrite 9 to the x as 3 squared to the x. And then at least the bases are the same, they're both 3. So now I've got, if I think about it this way instead, 3 to the 2 to the x is the same as 3 to the x squared. we've got 3 to the x. We want to factor it. 2 and a 3 with the 3 subtracted and the 2 added. So now we've got a product equal to 0. We can set each factor to 0. And go from there. 3 to the x equals -2. We've seen that before. That's impossible. 3 to the x will only be positive, never negative. 3 to the x equals 3. Well, that's easy. X has to be 1. So one solution only, x equals 1. And again, we could look at the equation at the start and pretty much just see that x equals 1 is a solution, but we want to be able to rule out any other solutions, and this is the way to do that. Next, we want to take a look at solving logarithmic equations. And a logarithmic equation is just an equation in which the variable is involved as an input for a logarithm. So looking at this example, log base 3 of x plus 4 equals 7, the x shows up as part of the input for that log base 3. So that's a logarithmic equation. Our general steps are to isolate the logarithmic term if we can, the logarithm and its input. If we need to, we can combine logarithms using logarithmic rules to get down to a single logarithmic expression. And once we've done that, we want to rewrite in exponential form. So this is the step where if we can't remember what to do, there's nowhere to go. So remember, we're switching to exponential form always in these equations. Solve for the variable and check for extraneous solutions. So we always want to look to make sure we throw out anything that would give us a negative or a 0 input for a logarithm. The inputs for the logarithms must be positive. So we'll be careful about that step at the end of each of these equations. Inputs for logarithms must be positive, not 0, not negative. That doesn't mean that x necessarily has to be positive. For example, in the previous equation we were looking at, if x were -1, -1 plus 4 is still positive. So we could keep that as a possible solution. So again, the inputs for logarithms must be positive. So this check step is actually really critical in this type of equation. We can do everything correctly and come up with solutions that aren't actual solutions. So looking at example 4a here, we're trying to solve the logarithmic equation. We want an exact solution and then an approximation to the nearest hundredth. In this example, the first one, we've got a single logarithmic expression and it's already isolated. So this is as simple as these are going to get. So right away we just switch to exponential form. Which the base is 4. The exponent would be 2 and we would get 3x minus 2. So go ahead and simplify 4 squared, that's 16. Add 2 to both sides. Divide by 3. And we get x equals 6. And then what we want to make sure is the input, the 3x minus 2, we want to know, is that greater than 0? Well, 3x minus 2, it would be 18 minus 2, and that is greater than 0, so yes. So we keep 6 as a solution. Alright, so the next one We have two logarithms, so we want to combine them into a single logarithm using the correct property. If we have a sum, we can put it together as a single logarithm with the same base of the product, which would be x squared minus 3x. So I'm multiplying x and x minus 3. So first get a single logarithm and then switch to exponential form. Which would say base 4 with the exponent 1 is x squared minus 3x. Now we've got a quadratic equation, so we want 0 on one side. I'm going to rewrite it like this: x squared minus 3x minus 4 equals 0. So then we'll factor x minus 4, x plus 1 will work. So then we'd get x equals 4 or x equals negative 1. And this time we want to check, is x greater than 0 and is x minus 3 greater than 0? And for x equals negative 1, no, that's a problem, but x equals 4 satisfies both. 4 is greater than 0 and 4 minus 3 is greater than 0. So that one is fine. So we get just the single solution, x equals 4. So you can see how this can happen. So we do the correct process, but one of the solutions that comes out of that doesn't actually solve the equation that was there originally. And that's called an extraneous solution. All right, so then example C here, we have the logarithmic expression isolated right away, so we don't need to do any combining of logarithms or anything like that. So we'll switch to exponential form. The only tricky part is that here the base we know is e, so it's not written, but natural log is log base e, so e to the 8th is x plus 2. And then we're pretty much done. Subtract 2. And grab your calculator because we're supposed to get an approximate solution. And that's not an integer value, so we need to figure that out. This is going to be quite large. E to the 8th. Take away 2. So 2,978.96. Roughly, let me double check that. 2978.96, right. So that wasn't a complicated example, just emphasizing that, remember, when it's natural log, it's log base e. So you would say e with this exponent gives me x plus 2. A bunch more here. They'll get kind of progressively more challenging as we go. Here we've got the the logarithmic expression isolated again right away, so we'll switch to exponential form. Base 5 exponent 2 would give me x squared plus 4x plus 4. That's quadratic, so we'll subtract 25 to get a 0. 4 minus 25, that's negative 21. We'll try to factor. Looks like 7 and 3 are the factors we need, a plus 7 and a minus 3. So we would have x equals negative 7 when x plus 7 is 0, or x equals 3 when x minus 3 is 0. And we want to check the original input, x squared plus 4x plus 4. We want to make sure that that's greater than 0. So we would check 49 minus 28 plus 4, that's positive, yep, okay. And 9 plus 12 plus 4. Also positive, so everything's good. So this time we get to keep both solutions. Because both of them make the original input positive. Notice the difference here. In example D, the input originally was a quadratic expression, whereas in example B, once we combined the two, we had a quadratic expression, but at the start, the original equation, they were separated as x and x minus 3. You have to always go back to the very original equation, not something where you combined the inputs. So you always want to check the original x and x minus 3 in this case, and x squared plus 4x plus 4 in the case of example D. Alright, then in example E here, we have logarithms on both sides. So what we want to do is clean up both sides as much as we can using the properties of logarithms. So we'd have log of x squared on the left side, and on the right side we'd have log of 6x minus 8 when I multiply these two inputs together. So using that property that says we can combine the sum of logarithms and make it the logarithm of the product of the inputs. And now if these logarithms are the same, their inputs have to be the same. So we're not dividing by the logarithm, we're just saying if two logarithmic expressions are the same and they have the same base, then the inputs have to be the same. So x squared must be the same as 6x minus 8. So we didn't switch to exponential form, we just said, well, if the logarithms are the same, their inputs have to be the same. So x squared minus 6x plus 8 is 0. That's going to give me x minus 2 times x minus 4 equals 0. So x equals 2 is one possibility, x equals 4 is another. And this time we want to check the original inputs were x and 2, which doesn't involve x, and 3x minus 4. So is x greater than 0, and is 3x minus 4 greater than 0? And for each of these, I think both are true. Certainly both are positive. 3 times 2 minus 4 is positive, and 3 times 4 minus 4 is positive. So yes, both of these would be valid inputs for the original. So we get two solutions. Example F is different from anything we've seen because we've got a composition of logarithms. On the outside function we have a log base 4, on the inside we have a log base 2. There's not a way to put these together, but what we want to do is work from the outside inward. So we want to undo this outside logarithm first. If the log base 4 of something is 0, we can first start by doing then 4 with the exponent 0 gives us the input on the inside, so log base 2 of x minus 1. So we peeled off that outside layer. We undid the log base 4 by saying 4 to the 0 gives us this input. The input happened to involve a logarithm, but that's okay, we'll just keep going. 4 to the 0 is 1. So now we have another logarithmic equation to solve. This time we want to undo the log base 2. So we'll switch to exponential form. 2 to the 1 should give me x minus 1. So if I add 1 to both sides, it looks like x will be 3. And this time we want to check, is x minus 1 greater than 0? It is. We also want to make sure that the log base 2 of x minus 1 is greater than 0 because that's the input for the second logarithm. So x minus 1 is positive, that's okay. And then this one, log base 2, that would be log base 2 of 2, which is 1, and that's also positive. So everything's fine. Example G is the trickiest of them here. We've got the log base 2 of 3x plus, let's change that 2 to a 4, minus the log base 4 of x equals 3. There are just a few problems like this in your homework where you've got one with a base 2 and one with a base 4. And they give you a hint. They say change log base 4 of x to base 2. It would be also fine to switch the log base 2 to log base 4. It doesn't matter which way you go, but since this was the hint that was given, let's do this. So let's aside here figure out how the log base 4 of x would be the log related to the log base 2 of x. So let's say if r is the log base 4 of x, just to put an expression or a letter name to that quantity, that would mean 4 to the r would give me x. And I want to figure out what exponent I would need to put on 2 to get x. And it looks like 2 squared would be 4, so 2 to the 2r would give me x. So I can see then that the log base 2 of x would be 2r. So the log base 2 of x would be double the log base 4 of x, which makes sense if you think about it. If you need a certain exponent on something to get x, on 4 to get x, you would need double that exponent on 2 to get x. But what we're trying to replace is the log base 4 of x. So what we have is the log base 2 of x cut in half would be the log base 4 of x. So what I want to do is replace the log base 4 of x with 1/2 of the log base 2 of x. So we'll have log base 4 of 3x plus 4 minus 1/2 of the log base 2 of x equals 3. So this is the complicated part, switching it so that, oops, just messed that up, so that each of them has a log base 2. The first one should stay log base 2, and the second one should switch from log base 4 to 1/2 times the log base 2 of x. Now that they have the same base, we can work on combining them. So we'd have log base 2 of 3x plus 4. We need to move this half out of the way, minus the log base 2 of the square root of x. Then we can combine these into a quotient. And then switch to exponential form. 2 cubed would be 3x plus 4 over square root of x. And then multiply both sides by the square root of x. So we'll have 8 times the square root of x equals 3x plus 4. And then I guess we'd want to square both sides to undo this square root. So 64x equals 9x squared plus 24x plus 16. And that's quadratic, so if you need to FOIL this out, you can, but this should be what you get when you expand that. 0 equals 9x squared minus 40x plus 16. You can try to factor that, I guess. I'm not sure what's going to work well here. We could try 9x and x, maybe. 16, we could do 2 and 8. That's not going to work that well. So 2 and 8, 10 and 6. That's also not going to work. I'm going to pause this and see if I can come up with factor. 4 and 4 will work for us, both with a negative. That's going to give us a plus 16 and a 36 and a 4, both negative in the middle. So let's work with that. So we get 9x minus 4 equals 0, or x minus 4 equals 0. So x would be 4/9, or x would be 4. And what we want to check is that 3x plus 4 is positive, and that x is positive. And certainly, since each of these is positive, then they're both going to satisfy both of those inequalities. So both solutions work just fine. 4/9 and 4. Okay. Then, the next example, we're being asked to solve some equations with our graphing calculator. And what I want to explain is how you would know that you're going to need your calculator for something like this. Notice in A, we have a combination of an exponential expression on one side and a polynomial on the other. When we have a combination like that, where we can't get a factor and equal to 0 kind of form, there's no way to solve this without graphical or what are called numerical approximation methods. You won't be able to come up with an exact solution without either a table of values or a graphing calculator. Same thing in example 5b here. We have a natural log expression on one side and a linear expression on the other. These are not the types of equations we can solve by hand. So let's go ahead and graph them. So I'm going to do the method where we graph both sides and then look for intersections. So I want e to the x as my y1 and x cubed plus 1 as y2. I'm just going to do the zoom standard first. And you can see that in that window, it's hard to tell what's going on. The graphs are all just kind of jumbled up. So I can see there are some intersection points here, but what I want to do is zoom in a little bit so I can see them more closely. So I want to adjust the window. So maybe I just do, it looks like maybe -2 to 2 to start with. So I'm going to do that for my x's. And I can do a zoom fit, and if it doesn't look that helpful, maybe I can adjust the y's a little bit. I think I'll do that. I don't need to see these negative y values, and I don't need to see them as high as I'm seeing either. So I'm going to adjust the y min to be maybe even just -1, and the y max to be 5, and let's see what we can see. That's better. All right, so that'll be fine. Okay, so this was x min -2, x max 2, y min -1, y max 5. Again, we just adjusted that manually so we could see these intersection points. And we can see in this window at least there are 3. So let's find them. Intersect, first curve, enter, second curve, enter, move closer to the one on the left. We get about -0.825. Then the next one looks like x equals 0, and that makes sense. X equals 0, we'd have e to the 0 and 0 plus 1. So we don't need to find that one on our calculator. X equals 0 would be the one on the y-axis there. And let's go find that third one that we can see. I'm just going to enter my guess as like 1.7. Looks like it's telling us 1.545. All right, and then we have to be really careful because there's another one that we can't see in this window. The way we know that is this. Exponential functions will grow more quickly in the long run than any polynomial. That's why when you're wanting to say something is growing really quickly, you say it's growing exponentially. That's the fastest growing function. So we know that at this last place where these functions intersected, the x cubed graph was going to be taller right there. But we know the e to the x graph has to grow more quickly, so they have to switch places again. The e to the x graph has to eventually be above the x cubed graph. So let's go look in another window. Let's move out, maybe just adjust it so that we look at past x equals 2. So change the window, maybe x min is 2, and these are going to grow quickly, so I'm going to do x max is 6. I'll try a zoom fit and see how it looks, and if we can't see anything, then we'll adjust it. But with that zoom fit, we can see. All right, so in this window, from 2 to 6 for the x's with a zoom fit, we've got this last intersection point. So that last intersection point, let's find it. Looks like x is about 4.57. So there are 4 solutions. We had to adjust our windows to be able to get them. But -0.825, 0, 1.545, and about 4.57. The next one isn't quite as complicated, so let's take a look at that. And the next one, the natural log of x, that graph, we know its shape. And x minus 4. We know the shape of that graph. Let's just do zoom standard and see what it looks like. That's probably of just a fine window. We know that this natural log graph isn't going to grow as quickly as the linear graph. So we know that this is actually going to be the only intersection point. So let's find it. Notice where it says first curve, there's not a y value showing up. That just means you need to move your cursor a little bit to actually have it be on the curve. And, oh boy, I wasn't looking carefully, was I? It's just telling us there is an intersection point over here close to the y-axis, of course, because the logarithmic function is going to drop down. It's got to cross that line y equals x minus 4. So one of them is at 0.0186 roughly for x, and then there is another one that we can see. So there are two. I wasn't thinking carefully. So let me capture that screen. So x is about 0.0187, we'll say. And then the other one move closer to, second curve, just hit enter, and then I guess you want to move closer to the other point. So about 5.749. So just those two solutions. All right, last example here in this section. So we've got if one function is given as log base 3 of x plus 5, and the other is log base 3 of x minus 1, we want to think about the following questions. First, we want to figure out where f of x equals 2. This isn't necessarily a difficult problem, it's just putting it together with the way it's stated and what are they trying to get me to do. What we want to do then is just solve the equation log base 3 of x plus 5 is 2. Okay. So 3 squared would be x plus 5, switch to exponential form. Looks like, oops, got to the answer in my head and started writing it. So 9 would be x plus 5. So x is 4. If g of x is 3 and we want to solve that, then we're solving log base 3 of x minus 1 equals 3, which would be 3 to the third equals x minus 1. So 9 equals x minus, whoops, not 9, that's 27. So x is 28. Then it's asking us, do these graphs intersect? And if so, where? So we would have the log base 3 of x plus 5 equals the log base 3 of x minus 1. If they intersect, these are the logarithms with the same base, so the inputs would have to be the same. Again, I'm not dividing by log base 3, I'm just saying if these functions are the same, since they have the same base, the inputs would have to be the same. And if I subtract x from both sides, I get 5 equals negative 1, which is a contradiction. So there are no intersection points. We looked at that algebraically. Another way to think about it is graphically. They're the same graph one is just shifted 5 units left and one is shifted 1 unit right. So one of them has a vertical asymptote at -5. I'm just roughly sketching this, and one has a vertical asymptote at 1, but it's the same graph, just shifted, right? So it makes sense that they don't have any intersection points. That one is always going to be a little taller than the other. So if f plus g of x is 3, f plus g of x would be log base 3 of x plus 5 plus log base 3 of x minus 1. We want to know where that's not 1, where it's 3. We could combine these two, so we'd have log base 3 of the product, which would be x squared plus 4x minus 5. And then switch to exponential form. 3 cubed is 27. Subtract 27 from both sides. It's -32, so we'll have 0 equals x plus 8, x minus 4. X equals -8 or x equals 4. -8 doesn't make sense because it's not in the domain of the first graph or the second. So we just get x equals 4. F minus g of x equals 2. We would have log base 3 of x plus 5 minus log base 3 of x minus 1 equals 2. Combine again, so we'd have log base 3 of the quotient x plus 5 over x minus 1, and that's equal to 2. Then switch to exponential form. 3 squared, so 9, equals x plus 5 over x minus 1. Multiply both sides by x minus 1. We'll have 9 x minus 1 equals x plus 5. This is just linear, so let's just distribute. 9x minus 9 equals x plus 5. Add 9 to both sides. Subtract x from both sides. 8x equals 14, so x equals 14 over 8, which is 7/4. 7/4 makes both inputs positive. X plus 5 is positive and x minus 1 would be positive, so that will work just fine. So hopefully that's a wide enough variety of equation types that you've got a good handle on solving these on your own. Good luck.